This is the result we ended with on Monday. For all graphs with no isolated vertices, alpha prime of G plus beta prime of G equals N. What the hell are alpha prime and beta prime again? Say again? The edge independence number. So that's which one? Alpha prime. And that tells me how many edges I can make so that nothing overlaps. Beta prime edge covering is how many edges I need to cover every vertex. And the play between these two is really the edges you are, the vertices you aren't covering with your edge independence are the ones you have to add an extra edge to. And then you use the other edges. I don't want to run through the proof. It's literally a counting argument. But everything we did for edges, I can turn my perspective around and do from vertices. So what do you think independent vertices are? Based on the idea of independent edges. What do I mean for edges to be independent? Oh, the definition is right there on the previous page of notes. Two edges are independent if that's us using the independent set of edges, and that's an edge, that's a maximal set of independent edges. That's a different thing. The edges are independent if they're not adjacent. They're not connected to the same vertex. So, two vertices are independent if they're not adjacent. We could say they're pairwise non-adjacent. So no two of them can be adjacent. Okay, Jonah, basing myself off of the description you just read, I want the largest possible set that does this, right? A maximum cardinality set that'll give me a vertex independence number. And clearly I will get a maximum independent set, the set of vertices with this cardinality. All right, wait a second. Let me think about the set of graphs we were using earlier. The cycle, the complete graph, and a bipartite graph. In a cycle, the end. Maximum number of independent vertices. If I had a triangle, right, I could only take one of them. These two would be adjacent. One of those two would be adjacent somewhere else. If I had a square, I could take any two diagonal corners. A pentagon, I could do, I don't know, 1, skip 2, do 3. I can't do 4, but because of 1, I can't do 5 either. So the 4 of n over 2 seems like exactly the right place to go for that. How about kn? Aha! Every vertex is adjacent to every other vertex, right? So as soon as I pick one, I can't pick anything else. They're all adjacent to it. What if I have a bipartite graph? A complete bipartite graph. So I have the set of R vertices on one side, the set of S vertices on the other side. Oh, and in the versions we were doing on Monday, R was smaller than S. What things are going to be independent here? Vertex-wise. Whatever vertices are in that size of set S, right? Because none of them are adjacent to each other. They're all adjacent to the stuff on the other side. Okay. From what we did on Monday, I came up with an edge independent set. Then I came up with an edge cover. An edge cover meant I had a set of edges that covered every vertex. What's a vertex cover? Because the edge covers the vertex covers the edge if they're adjacent to each other. Okay, I want to use the vertices to cover all the edges. Again, I wanted the biggest possible set of independent I want the smallest possible cover. Hey, wait a minute. I called the edge covering number alpha of G. I'm sorry, edge covering. I called the edge covering number what? Alpha of G was the vertex independence number. So I'll just call this one beta. Which means to me the book introduced these in the ass backwards order. You would think beta comes before beta prime and alpha comes before alpha prime, but no, I didn't write the book. I think the idea of a vertex cover and a vertex independent set came before the idea of an edge cover and an edge independent set. But since the edge versions are more closely related to matchings, this book introduced them first. Same three graphs. Why?
If you have a triangle, you have one, the top would be one, that would cover both of these edges, so you need one more to cover the bottom edge.
Sure. In any triangle, I can cover the top two edges with the top vertex. I need one more vertex to cover the bottom. Go to a square. The opposite diagonal corners each covers two. A pentagon, the same way we said, I have to skip one of these, now I have to add one because I need, going around the pentagon, I need to cover one of those vertices to get that edge. So yes, ceiling of n over 2. Hey, wait a second. Floor of n over 2, ceiling of n over 2. How about Ka? It's one vertex because I can't touch anything else because they're all adjacent. But now I want to cover all the edges, right? I need to cover every edge. If I only use one vertex, I've only covered n minus 1 edges. Everything has degree n minus 1. I need more. I'm sorry?
Would it be the same thing?
I think I still need more. Let's think about that one vertex. That one vertex is connected to everything else, right? But all of those are connected to each other, aren't they? Which means each of those vertices already covers the edge back to this one. So this one vertex is the only one I don't need. It's n minus 1. Hey, wait a minute. What do you think it's going to be here? The smaller one. The sum of the edge independence number and the edge covering number is the order of the graph. The size of the vertex independence number and the vertex covering number is the order of the graph. Those two theorems put together are called the Galli identities. And on page 191, there's a small table. That reminds me what each of those four things are. Put a Post-it note there. Here's a graph. 2 copies of K3 added to a single vertex, K1. You add graphs, you connect the vertices of one to the vertices of the other. All right, let's see if we can figure out all 4 of the numbers for this. You want to start with edges or vertices? Okay. Starting with vertices, W is adjacent to everything, right? So if I include W in a set, I'm done. That's already covering all the other vertices. That's a problem. In a vertex independent set, I'm done. That vertex shares a vertex with everything else. Can't use it in an independent set. But I can cover a whole bunch of edges with it. So it should go in one and not in the other. Now I know which one it should go in. As soon as I include W, I can't include anything else. All of the other ones are adjacent to it. So that's not going to work. Wait a minute. What other thing is special about W? It's cut vertex. It's a single, because a vertex cut is a set of vertices that but it's a cut vertex. I can disconnect with one. Oh, okay, well, wait a minute. If I disconnect it using that cut vertex, then I end up with 2 triangles. That's CN. How many vertices do I need to do C3? So the number of independent vertices or the number of vertices in a vertex cover? Which way are we doing it? Because if we're doing covering, okay, I need to cover all the edges, I need 2. If I'm doing independence, I can only do 1. So in a vertex independence set, I would pick 1 from each triangle. Ideally, not the one directly adjacent to W. So either U or T, Y or Z. And then I could pick W and have an independent set. But I can only get 1 from each triangle to do independence. If I'm doing coverings, I need 2 from each triangle. But W already covers a whole bunch of other stuff, doesn't it? Really, I can make a vertex cover from 2 of each triangle and the 1 in the middle. Hey, wait a minute. 2 from each triangle and 1 in the middle versus 1 on each triangle. And that tells me right there that alpha of G is 2. The most independent vertices I can get. How about edges? Let's look at a set of independent edges. Oh, wait a second. Independent edges, they can't share any vertices, right? In K3, how many edges should I use? Floor of n over 2. So I should get 1 from the triangle over there on the left. 1 from the triangle over here on the right. Can I get anything else? Trying to keep the picture with me here. So I could do, say, UT, and I could do YZ. Could I do something else that's not adjacent to those as an edge? Sure, I could do either do WV or WX. And none of those touch each other at all. Can I get anything else onto here? Nope, it's going to be adjacent to W somehow, right? I'm in trouble. Or it's going to be adjacent to U and T, or adjacent to Y and Z. It's either going to come from these two, or these two, or it's going to be coming from one of those six. Hey, wait a minute. That's the independent set. There are three there. So how many in my edge cover? Exactly. Because I have to add up to n. So, same question. What four edges cover all the vertices? I don't know what movie is screaming in the background there, sorry. Right down there, my set of independent edges is only missing x. I need something to hit x. That's it. Whatever vertex you want that hits x. Sorry, whatever edge you want that hits x. Which gives me 3 to choose from. So if I'm not dealing with a cycle, a complete graph, or a bipartite graph, there isn't an obvious algorithm to find these things. But another way to think of this, my set of independent edges is a matching, right? It's not a perfect matching because I missed x. Matter of fact, I can't have a perfect matching in this graph because it has an odd number of vertices. I can only have a perfect matching in a graph whose order is even. But in one sense, any perfect matching, any matching at all really, is a subgraph of G. What's special if that's a perfect matching? There's another adjective I can add to the fact that that is a subgraph. I have a perfect matching. What adjective can I add saying, oh, you've got a subgraph? Yes, every matching is bipartite. There's another one. You're not wrong, but I'm looking for something else as well. And it comes from the fact that it's perfect. Because this matching is a bipartite graph, yes? But it wasn't a perfect matching because we missed X. Spanning. Ha. And since it's a matching, it's a copy of a bunch of T1s. Two vertices with one edge, which makes it one regular. A one regular spanning subgraph is called a one factor. Which means I have a one factor if I have a perfect matching. And only if I have a perfect matching. Okay. Every even cycle. Yes or no? Does any even cycle contain a one factor? Why? What wouldn't be onto? um, I don't know how sets are onto in the first place, so I'm still a little confused at which training. So I create this bipartite vertex set, and I'm claiming that there'll be n over 2 in one group and n over 2 in the other, and all of them will be connected. How do I know that's going to happen? In the Child Development Center, kids are sitting in a ring, walking around tapping their heads. What am I playing? What game is this? Y'all were children once. Yes. I'm playing Duck, Duck, Goose, right? And I'm going to pick one kid, run around and sit in their spot, right? Okay, wait a minute. Just tap them and go 1, 2, 1, 2, 1, 2, 1, 2. It's got to divide them out, right? Everyone holds hands with a 2, but then not the 2 with the next one. There's my matching. Tell the kid only to hold the hand of the number greater and to the left. I've created a matching. And it's a perfect matching because there's an even number of kids. And every edge I left out is a different perfect matching. Just draw the square. Let's do an example. I want a perfect matching. Which way are you going to draw the edges? Say again? Okay, there's one perfect matching. But since I'm looking at C4, the other two edges are this way, aren't they? Ta-da! There's your other perfect matching. You should be able to write a very straightforward inductive picture argument. Not really even a proof. If I want to do it for C6, well, I'm either going to do the edges between 1 and 2, 3 and 4, 5 and 6. I'm going to do the other set of 3 that I just left out. 8, 1 to 2, 3 to 4, 5 to 6, 7 to 8. Or the ones I just left out. It's a guarantee. Does Kn contain a one factor? Because even if I ignore the rest of it, Cn is a subgraph of Kn. There you go. Again, let me pick graphs we've been working with. A complete bipartite graph, KRS. Draw some pictures. Pick some values for R and S. Draw KRS. Use small ones, 2, 3, 4. I'm not talking about anything huge. You should be able to come up with a when it has one or when it doesn't. If they're the same number of spots on the top and the bottom, then I'll be able to go straight up and down. If there's even one difference, well, two difference, right? Because I have to have an even number of vertices, then I can't do it. Perfect. Let's pull another graph out of thin air. How about the Peterson graph? What's the Peterson graph again? The star with the pentagon around it, and they're connected. Do you see a one factor? Which one?
Everything assembly.
There you go. As a matter of fact, I even numbered the vertices when we were talking about the Peterson graph. I numbered the outside as O1 through O5, and the inner ones as I1 through I5. So I'm really going OI to II, outer to inner, directly across. There's our one factor. Page 195. Look, a bunch of 3 regular graphs. There's our Peterson graph at the top. They used U and V instead of outer and inner. I don't care. The K33, K4 at a bridge in the middle, K4 and some weird diamond in the middle. I've seen this one before. No, I've seen that before. Oh. That's we had the 2 on the outside, so it was a hexagon with 2 bars across the middle and a bar top to bottom. This one. These all have 1 factors. Some of them contain more than 1. So for example, here I can go 1, 2, 3. I can also go 1, 2, 3. I can go straight up and down, or I can mix and match, right? I have several different 1 factors there. This does not contain a 1 factor. Somebody tell me why. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Sorry. It's even. Yes, but why is that the problem?
I was trying to go around and you can do like V1 to V and then 2 edges that would make that first like upper left one matching. But if you go over to the right one, you can't use V2 and V because it would have repeated V, so then you can't make them matching in that one.
That cut vertex is adjacent to 3 things. Means we need to take one of those edges and leave the other 2 as unavailable. And if you throw away those 2 other edges, then you've got subgraphs that are odd. So let's say I was going to use V and V1, then these pieces are all fine, but that's a graph of size 5. Sorry, order 5. And that's a graph of order 5, and then I'm screwed. I can only have a perfect matching if my graph order is even. Well, so one of the bigger questions is, when do I have a 1 factor and when do I not have one? Because right now, the only thing I'm sure I need is I need the order of the graph, call that n, must be even. But clearly that's not enough, because the example we just looked at had order 16 and was screwed. It can't just be the presence of cut vertices. Let's go back and look at page 195 at some of the ones on the top of that picture. In the top of that picture, these graphs have bridges. Since they have bridges, they have cut vertices. But these graphs have one factors. As a matter of fact, here, if I take the bridge, then I've left a subgraph of order 4 on the top and a subgraph of order 4 on the bottom, and that's perfectly fine. If I take the bridge here and the bridge here, same deal, and I've left a subgraph of order 2 in the middle. So all of my pieces. Wait a minute. We had a name for those. What do we call those pieces? Well, I need to do something about blocks. Maybe that's it. Maybe. That's only a maybe, because the blocks were of order 5 in that one, but I don't know if that's going to be true enough for all blocks. All right, wait a minute. Cycles always contain a one factor, if they're even. What kind of graphs do I know always contain a spanning cycle? Yes, but there's another one. Lots of not complete graphs contain spanning cycles. Any graph that's got a Hamiltonian cycle, I can then just imagine that cycle, ignore all the rest of the edges, and say, there, I have a cycle of size n, and is even, I have two factors. Sorry, two one factors. I want to make sure I talked about them correctly. Okay, wait a minute. We had properties about Hamiltonian, right? We knew if a graph was Hamiltonian, then we knew things about it. So let's jump back to the chapter on Hamiltonian stuff. That's in chapter 6. What do I know about blocks and components and things that happen in graphs that are Hamiltonian? I've got 30 seconds left today. That's where we'll pick up on Friday. So between now and then, go look at what do we know about components and cut vertices and things like that in Hamiltonian graphs. Chapter 6, section 2. I will see you all then. Have a wonderful rest of your day.